Hello, everyone. Welcome to the seminar. It's my great pleasure to introduce today's speaker. Romaric is an associate professor at Chalmers University of Technology. This is in Sweden, in Gothenburg. Very nice place. So Mike has been visiting BU for the past month. Actually, he's been around for the month of October. We couldn't find another slot, so unfortunately, we have his talk during the last week of his visit, but you still have 1 day, 2 days, Nicky, today and tomorrow. So if you're interested in talking to him and you haven't yet had the chance, let me know or let Romaric know. So Romaric is doing a lot of interesting work and he has broad interests, I guess like myself, that's why we realize we have a lot of common overlap. So he's doing research in distributed systems, federated learning, security, graphs, yes, among other things, edge computing, right? Yes. There. And his visit is part of a European project, European initiative, I guess, for faculty from Europe to visit US institutions for a short time. So that we can start making changes. So yeah. Thanks for giving another talk. So you gave a talk at the security seminar. So yeah, thanks a lot.
Thank you very much, Vazia. I think I can just start by I'm happy to be here, and a bit ashamed this kind of at the very last week, but I think we got a very nice and productive notes for quite a few of the students. Much discussion. So I will start just by continuing a bit on Vazia's introduction. I'm from Chalmers, so that's in Sweden. It's in the south of Sweden, but it's still very cold, of course. My background is in more theoretical, I would say, theoretical computer science, discrete math, also formalism of distributed systems. It's like around 8 years I've been at Chalmers, and since that I've moved to Chalmers. I think I've applied my theory much more on applied results, on concrete applications. I will give a few examples first. And now I do a little bit of a mix of try to see how can theory help drive new application, new results, and try always to keep a foot on both sides, because I think they are both interesting. That's my point of view. And one of the red threads in my research is to focus on problems where you can design more efficient algorithms based on the data that you have. Not studying the algorithms in the worst case, because in all the applications I've been working, it's never the worst case you see. It's always some data distribution that allows much better algorithm to be designed. And often on those ones, greedy algorithms are very good. And in theory, the worst case of greedy are really bad. And so one of part of my research try to understand this and try to still give formal guarantees for this algorithm. And I think you need to introduce some kind of assumptions on the data. That's why I call it this data-driven analysis. In terms of applications, it's around distributed systems, algorithms, communication. At the beginning, I've been working quite a bit with vehicular networks. So I can introduce a few examples. I think that will talk now. I've been working with data compression. So one of the work is PLA compress. So this thing is basically compress signals in a streaming fashion. So you don't have to batch, compress, and send, but you can continuously compress the signal as it is produced. There is a C implementation there in that GitHub. Actually, that's really fast, even though here, and lightweight. So this is typically for what we tested. It was for a vehicular network scenario. You can have a look if you're interested in that, or we can discuss about that after. I've been working on something called data localization. It means that you have a vehicular network and you want to localize in the network where is data that's relevant to you. And here there's a trade-off between how much computational power or burden on the network you will incur, and how fast do you want your results. I've been working in the last around 5 years on the side on smart grids, so that we shift to really different domain. One particular application I've been looking at is that you have a set of households, they have some kind of batteries, so like energy resources that they can share with each other. And when they share, they can optimize their costs. So one thing I've been working a lot is this kind of matching problem, so forming those groups. The problem, you can analyze it in a theoretical way and show that it's very hard to solve. It's very hard, it means NPR, of course, but with huge number, huge company. What we propose here, again, is really algorithms that work really well, and we have analyzed them, and we can show actually that they give a bounded approximation on real data. I gave earlier, so that there is a library here that does this matching efficiently. It does a lot of things. It does a lot of optimization. And to finish this overview, I gave a talk a couple, 3 weeks ago or something, on security in the BU security seminar, and it was on video fingerprinting. And the idea was we have shown an attack that is like the largest to scale attack on video streaming services in terms of privacy. So we were able to recognize basically just based on network capture any video streamed on I think we picked Amazon Prime, HBO Max, and the Swedish service. Everything is open source there. You can also have a look and we can discuss if this is one for you. And today, what I decided to talk, instead of, because it's a lot of different directions, I thought it's lunchtime, maybe not so digestible to have so many different things. I thought I will present one recent work that we are working right now on it. It's about distributed monitoring. And I thought as system people, you might have some feedback on that. For now, the talk, the thing that we call is FEDAMON, and we call it an approach because we validate that this approach is very good, and I want to convince you about that. And the next step will be to make it into a system and then show that in practice is also good. Okay, so let's reset to 0 and let's say what are the settings we are talking about in this. So you have a lot of sensors. Here we'll just show vehicles, I don't know, servers, houses or whatever. They produce a lot of data, of course. But what you want to do in this setting is to monitor them. So basically every, let's say, second, half a second, whatever is your frequency, you want to know what is the reading on the sensors. Why do you want to do that? After that, there are some applications that will use this data. A few examples: anomaly detection. You can do network traffic analysis for vehicles. You will be interested in traffic flow management, or you do some kind of optimization. Anyways, a lot of things that basically are based on this monitoring of the system. The problem is, of course, if you have a lot of sensors, we are talking 10,000, I don't know, very large systems, of course, you will use a lot of bandwidth just for this monitoring, while a lot of data might not be really useful and might be redundant, possibly. This problem has been studied quite a bit, and a lot of the solutions that exist, usually they target for example, one particular application or that you want to run, and then you do something specialized for that application. And usually this works well, but then it's specialized for that. In this work, we took a different approach. Instead, we say, can we try to get a generic solution for monitoring that works really well in general, and then you can do any application you want on it. So the problem, you can formalize it like this. So you have a set of nodes, you have a coordinator. In general, in distributed monitoring, you want to compute a function f based on the values that are read at the nodes. Here, the values, they are read at discrete timestamps. If there are different ways how you implement that, if it's something that you read or if it's the average of different readings. but here we assume they are read at discrete timestamps, and you want to compute a function f on the values. And here, what we will focus, so instead of proposing a system for a particular f, we'll just forget that there is a function f and just monitor the values themselves. And we want to do that in an efficient way so that afterwards, just plug any f that you want, any function. If the monitoring is good, that will be good. The only assumption is that that function is not dependent. If you can tolerate a small error. So it's a function that can tolerate a small error on the values and that will not affect a lot of the function. Let's say, for example, if you want to retrieve the max or some quartiles, some distributions, you don't care of the exact values, perhaps, but you can tolerate a small error on it. If you cannot tolerate actually any error, then you cannot anything smart here. You have to transmit everything. Yeah.
It seems like a step backward from consensus and from this entire body.
Yeah.
Try to do as much as possible on the edge, right?
There are some overlap though, because you will see the approach that we have taken, and you'll see in some flavors it is compression. It's compressed in the flavor.
Okay.
You'll see. Okay, so we stay general, and then you can plug any function afterwards. Okay. And our baseline here will be, of course, sending all the values. So every single round, you send the values, and so we want to try to beat that. Can we be much more communication efficient? Here, the target is not that much on the computational power complexity, but more on the communication complexity. Okay, so the approach is started by error bounded. So basically, we tolerate an error. Actually, we have started another work where we show that if you cannot tolerate an error, then you cannot do anything smarter than just sending everything all the time. This is the worst case that we want to deviate. So we can tolerate an error. That means that basically the sensors, they will read a value every timestamps, and we also use predictions. So it means that we'll have one model. So here in this setting, we have one prediction model running on every single sensor node, and the same prediction models running on the coordinator up there. And then, thanks to this prediction model, we can do a prediction of the value. And it means that to be error bounded, it means that at any given timestamp, my prediction cannot deviate more than a fixed constant. Here it's fixed, a fixed constant of my real value. So I have a kind of guarantee. Let's say you're never beyond 5% of your value, or 1%, 10%. This is a parameter. Yeah. Please.
The prediction model, how can you predict, if you can predict ahead of time within 5% error, you don't even need to send anything, right? Seems like a very strong requirement. If I can predict the stock market, I can make a lot of money.
Yeah, I mean, you will see how the prediction models. So the prediction models, they use the previous values that you read, and then they predict the value.
Okay.
So of course, they cannot use the real. They cannot use the real value because you do the same prediction on the coordinator. What you want to say here is to have to transmit that value. So basically, you do the prediction on the node, you do the prediction on the coordinator, and if the prediction on the node is good, you don't transmit. And you know that the coordinator has an estimate that is not bad. And you do that as long as the basic idea is this, as long as the prediction is good. And when it's bad, you will see there is an update. You break the error, you update the coordinator. So basically, yeah.
So for different metrics, so some model maybe perform good in one metric, some model is good, bad in this metric. You think the dynamic changes the model, prediction model?
Yes, of course. That's exactly the approach we are taking. Yeah.
I just wondering if we can adjust the sample rate based on the error.
So here we assume that basically the sample rate doesn't have to be fixed overall, but for each node, it
If
comes
the error
at
is
regular
high,
interval.
so we
Then
adjust the
you
sample.
will have something behind that generates a value. This is kind of orthogonal, like how you generate those samples. They just come at regular interval, and that's the thing that you want to monitor.
Yeah, but I'm just wondering if we
Yeah.
can lower the sample rate and just
Yes.
something like that.
Very good question. So actually, this is adaptive sampling. So here in this talk, I don't really cover, there are many approaches for this. This is one of them. I think we argue why this can be good in some cases, in some others it's not that great. But I think here in our talk, it's kind of orthogonal because you can still plug that approach to generate those values. But this will be our ground truth, and then we want to monitor this. So you define what is your ground truth that you want to monitor.
And you don't make use of any relations between these nodes?
No. Here, the nodes are independent. So basically, you could see that. Yeah. So that's also a difference with work that the nodes, they have correlations, and then you exploit this. So here we try to stay general. So here we don't assume correlation. So what do we do? So each model has a buffer. So this is too simple. Each model has a buffer, and we'll use just a sliding window of the recent values to do the prediction. And what happens when, so if the prediction is good, nothing happened, basically no communication. If the prediction is bad, what happens is that I send that buffer to the coordinator. So that's what we call an update event. Okay, and then the coordinator can update the model based on that buffer. It's we analyze a bit different strategy here. Instead of sending a buffer values, you can send some kind of parameters. It happens that in the model that we have chosen, they are really lightweight, and sending the values are more efficient. On top of that, it gives the ground truth to the coordinator for calculating which model is good or not. You see when we change model. Okay. What are the models that we are using? So I'd say we wanted to keep them lightweight and efficient. Is basically otherwise you ruin the full point of having an efficient monitoring. If you have complex models running on the nodes and you save bandwidth, then you just spend more on energy just computing these things. So you want to have the very lightweight models, but just good enough that they can reduce your communication to a large extent. So this is the list that we integrate in the current system, but actually it's not really the main focus. You can just add more. We focus more on the approach itself. I just go through quickly, but I don't in detail, just to say a flavor of it. So simple approx, that's the simplest approximation you could get, is basically you just take it's constant. You read the value, and then my prediction would be that value for the time being, till it breaks the error, and then I will update the coordinator. So if you look at the view at the coordinator, it will be a staircase, basically. Every time it would just get an update when the deviation is too far from the last time I shared the value. This is used actually in some previous work as a baseline, so we also use similarly. Autoregressive model is just a linear, basically, model. What is the difference between another one that looks similar to LMS is that this one will have a larger buffer of values, K, to optimize its own parameters, to do a linear regression of the values. And I'll use a smaller number, L, to calculate the estimate. So the estimate is based on, let's say, the 10 last values, but I use 50 values to calculate the parameters inside the model. So I use 50 values, calculate the parameters, and then I use the 10 last to do the prediction. LMS is similar, but it doesn't use this larger buffer, only use the 10 last values. And so that's a bit weaker model, but it uses less values here. PLA is a bit different from the other one because this one doesn't require the previous values. The previous prediction to do the next prediction, it just take the best fit line on the, let's say, last 10 values, take the best fit line and just, this is my prediction. So it just always goes in the same direction. And then the whole linear and the whole winters, what is basically exponential moving average, exponential weighting moving average of previous values. The winters take some kind called seasonality, so there's a bit more values than the whole. But as I say, the models themselves, they are not super important. All we want to have is a lightweight prediction model that gives me a prediction very fast and uses few values, few of the recent values. What is the main metric I'm looking at? Well, something that we call the communication ratio. Is basically I take the number of updates I'm sending to the coordinator, and I look at what is the ratio compared to the worst case here that will be sending all the time all the values. What we call the baseline monitoring. Okay. And I got a question already earlier on. It was about here, I think it was about, yeah, but the models, they need to change over time. This is a very good point. So this is just an example of real data where you just run 4 models. So here it's just one model. You have 4 nodes, you run 1 model per node. What you already look is that actually these things already work really well like this, because in the sense that we already cut 97% of the computation just by doing that. It's because if you look at the real data, it's very predictable. You see, like this is like CPU usage on some kind of evolved packet core. So this was with Verizon actually, but it's very predictable. So of course, if you put a prediction, then you save already a lot of computation. But what you can see as well is that if you look at different period of time, here in the first period here, one model, the simple approx was not the best. Is I guess obviously the data increases. So if you just stay constant, that's not great. On that period, PLA was giving the best in terms of communication. And then there's enough. If you look further on data, it will be funny enough, it's the opposite. So it means that basically the best model, they change over time. So what the core of the work is to propose an approach that we can update the model over time. So how do we do that? So instead of running one model on the coordinator, now we run a set of candidate models. The thing is that we don't want to overload the node. So the node itself only runs a single model. It runs the active model, the one that will create a prediction. So the coordinator knows what is the active model, calculate the prediction. So it starts by the simple approx. And when the current model breaks, I receive the update as usual. But now when I receive an update, what I do is that I will simulate all the other models with the data that is inside the update, as if both models were run on the node. Almost, I have to present, almost as if, because actually when the current model is very good, I don't send a lot of updates. So actually there might be data completely missed. So in that case, I cannot of course simulate, but I use, at least since the buffer is the last data, we think that is the best data to use to evaluate this set of candidate models. And then my scoring function, I take 2 things into account. I take both the accuracy of the model, but also how much communication was saved. And I can tune the system if you're more interested. For example, if I want to have the model that just gives me the best communication, so the lowest number of messages, then you can select that one. But you can also kind of take a bit of a trade-off and say, okay, perhaps that one gives a better accuracy. So I'm selecting this one. And it has also a good omission rate. Okay. So you calculate the best, and then once you have the best, it's easy. There is a small threshold to pass, and then you have the best model here, and then you can send it to the node. So now you have a new type of message. Is you switch the current model on the node. Okay. Nice, and everything is node-wise. Yeah, how to determine the candidate models. That's a new thing because actually from the very beginning of the talk, we want to stay general. Actually, not only we want to stay general, we want a solution, a plug and play solution. We want something you just activate and then you start, you don't know anything about your sensors and it will already save your communication. Really, is it feasible? Actually, we'll show that in the data we have. Yeah, if you just set a set of coordinate models that covers some range of buffer size and behavior, so a few autoregression, a few LMS, some PLA, the simple approx, etc. We have just 10 models, and actually this gives a very good performance, even on data that's never seen, because it covers a wide range. The only assumption that we have is that the data is not random. The data is not just for some random values, it has some kind of time correlation, and then this system, this kind of standard system works really well on those data. I'll show a little bit of results. So that gives automatic control. There's still a last parameter here that you have to tune for now that I haven't talked that much, is this error. The error was fixed. It was like I tolerate exactly this absolute error on my sensor node. But actually, we have also introduced, there's something else behind the scene, is that the nodes themselves, they have a buffer of values where they will calculate the range of those values, and then they will calculate themselves what is the error they can correct. The coordinator cannot do that because it doesn't know those values. So this is calculated on nodes. And then once you send the update, not only you send the update, but you also send, oh, this is my error, this is my local error. And then the only parameter that you set in that system is how much of the range of the last, let's say 1,000 values or 100 values I can tolerate. And this is just, you can say 5, 10, 15. And then everything is node-wise independent. You know? I think I gave you the main point, but this is system talk. I need to show a big overview that we cannot read and that too many information on it. But just to say that I think I mentioned all the different buffers. So they are, each node runs a model that has its own buffer, and then the coordinator needs to simulate all the models. So for that, it needs to remember both where the state of the model, because the model might be in an old state, and it needs to remember when I give real values, basically I cannot give them to the model. I have to simulate a node reading those values and just checking if it breaks the local error, and then simulate an update of the model once it breaks the error. So I have a state for every model, and I also remember I have sliding windows basically for the errors and the number of messages to calculate the score on every model. Yeah, actually it's present. I think time for some evaluation. Yes.
Got a quick question. So since you only bound the error on the node, you only send an update once you're outside of the error.
Yeah.
If your input signal starts to drift, you can be arbitrarily far away from what your coordinator thinks. Right? Because you have this buffer that is of finite length.
Yeah.
And as long as within the buffer you stay within the error rate, there is no problem.
Are you talking about the dynamic error, right? So this case, so you have your, so this epsilon basically was shared with the coordinator. It's an absolute epsilon. It's an absolute epsilon. So that was shared. So basically you calculate the range of your values, 100 last values. You calculate, you have a parameter 5%. So you calculate 5%. During the last update, this was shared with the coordinator. The coordinator knows this absolute value. So the view that is every single round at the coordinator and at the node is exactly the same every round, at least for the model that is the selected model. The other model, they are only updated once I get an update. So they are a bit synchronized. Yeah, does that answer?
I guess, yes.
Yeah. Okay, so a bit of evaluation. 4 very different data sets, I think, in flavor. So you can have CPU usage, speed of vehicles, temperature readings, energy consumptions here. I mean, you can plug more. It's just a matter of time, basically. In our simulator, we compare different behavior. So one is basically we have only a single model. One is this data-aware solution that has this standard model set, these 10 fixed models, and look a bit at the trade-off. And the main metric here is the communication ratio. And we look a little bit at errors, but errors, they behave very similarly, we see. Because of this error bound, you will most of the time have very close error on average. Okay, so this is just an example of the picked from the evaluation. The other, they look relatively similar. What we can see directly is the trade-off between of course, that's what we expect, the error and the communication ratio. And if you set the error, let's say to 2%, so it's an absolute error, 2% of here in that settings, we look at all the values. So we just wanted to have something comparable. So we look at all the values, you look at the range, you take 2% of that range, we remove a few outliers. And then you look, in that case, with 2% error, you only send 10% of messages. And if you tolerate a little bit more error, of course, very quickly you have something around 2-3%. Nice, and you see the error are relatively similar. Okay, so this the different models. Here is for one data set. You see, depending on the data set, usually the sensors, they behave relatively similarly in comparison to the models. Depending on the data set, one model often is a bit better. But what we wanted is a generic plug-and-play solution, something that will work whatever the data set, right? So if you look at the average performance of the different here prediction model that I presented at the beginning, this data-aware standard solution not only gives a good performance, but on average gives the best performance. That means that if you compare to the second best, so here in the data set that we had, the best of the single model performance was autoregression. And if we compare to that, we can improve to, you see, 7% communication. And being completely plug and play. So this is a kind of on top of not having anything to set. Because the parameters inside of data aware, they are fixed. They are fixed. They have been designed based on some kind of subset of these data sets. So we have also validated it on some data set that has not been seen, and we have roughly the same results here. It's also the best on average, because models cannot be good every time, right? So if you look at this alpha, we're saying like we can kind of tune the trade-off. What kind of things we can obtain is basically, in our experiments, we saw that you can get the same communication ratio, but you can improve the accuracy by just changing that alpha. Here, if you put alpha to 0.5, we get at 0.1% perhaps the same communication ratio, but we improve a few points of percentage of error. So we have something that doesn't use communication, and on top of that is pretty accurate. I think I didn't put that many. The last thing I wanted to say is about the dynamic error control. So basically what we had here is to check if we look at this dynamic error that's calculated on every node, and then we look what it looks like is something like this. So you just plot what's this dynamic error. It's also normalized by the range so that we can compare different data sets. What we see is that it's relatively focused. So every node will have relatively the same error. And if I take this, let's say, so here we have 3 levels. So the high level is 15% max. We see that most of the time the nodes are around on average 11% of the total range of all the data sets. So it means that if I plug that 11% and I run after the system with a standard fixed error, so let's say I already know my error, so I will run. Actually, what we show is run very similarly to the dynamic one. So it means really you will have the same performance, but without looking at the data. Because kind of this validates the dynamic error calculation. And on top of that, we also show, I think on that plot, we wanted to highlight is that, do you really save a lot by doing this data aware thing? It depends on the data set. On some, you will just get the best, but you will not save a lot more than simple approx, because the data more or less changes unpredictably somehow. But on some data set, like around that one, you go from 50% communication to around 10%. So you do some, I think you can really save a lot, at least on some data. But I think our main thing that we want to highlight in this work is this: you can do this really plug and play approach, generic. You don't have to do something specific to a function. You already are under 5% communication perhaps, and then you plug anything on top. I hope I convinced you that, yeah, that sounds great, and we need to push it to the next step, right? It's data where it's standard, and then the only thing left, it's integrated in the current. Yeah, that's it. Yes.
I wonder if you tried any running this with any data sets that have like periodic patterns.
The speed is rather periodic. So do you mean like very periodic, or?
I mean, where the value, let's say they have spikes, like the value increases and decreases, like, but they have like a pattern.
They stay in the same zone, right? That's what you mean.
Yeah, so I'm thinking of a case where your data like changes over time, and this change is longer than your window length.
Yeah.
So that even though it's kind of predictable, like your signal is kind of predictable, because your window length is very short, then you won't be able to actually realize that it's the same signal I'm sending over and over again. And
I understand. I think the closest I have in mind, I mean, I didn't look at every detail about the data sets, but closest I have in mind is the speed. The speed is something that doesn't go to very high, goes up, goes down, goes up, goes down, and it's regularly. It's not synchronized, but it's regularly. And I think that's where the data aware is the best. It's because it runs with different model that has different buffer size. So there is quite likely that in that one, I think the best would be the seasonal one, perhaps, or one of the halts that have a relatively large window that will capture this old dependency.
Right. Okay, so the window needs to be.
Yeah, some of the models, I don't have the parameters are in the paper, but it varies quite a bit. It goes from, I think, 5-6 values of window size to around 50-60.
Right, but you could have, let's say, diurnal pattern, right? During the day, and then during the night, that you would need a huge window for that.
Yeah.
So basically, I was thinking your coordinator.
Yeah.
Does it keep like history of? No.
It doesn't need it, but you can. But it doesn't need it. Yeah.
Okay, so you assume that your coordinator just keeps a window as well,
or
does it have access to historical values? It could, right?
It could, but we only use the recent values for the prediction.
Your coordinator is, I don't know, in the cloud, so you can assume that it has like unlimited compute possibly, or.
Yeah, even though here it's relatively light, that what he has to do is 10 models.
Yeah, I mean, I was thinking whether you could do the opposite kind of communication, like have your coordinator actually take historical data, then send some sort of a signature to the node and say, this is what I predict for the next period, unless your signal actually changes considerably, like don't send me anything, because I expect this to be, like I've seen the history, it seems regular. Like don't keep sending me values or something. Like,
I mean, we could test against that. I have the feeling it's quite specific in this case that it will work. Here it's very generic. I think that you just expect that the values are time correlated, and then you just predict a short time, because you don't want also not to send values. You want to send values at some interval. You know, so that the coordinator gets the update at the end that is really very close to the actually real values. But just in the meantime that you get your update, for example, you get an update every 10 minutes. But in the meantime of those 10 minutes, you had a very pretty good forecast of what the real values were. But yeah, I think in that use case, we might have something ahead of time.
Okay. Yeah, thanks.
Yeah. Yes.
So I have two questions. The first one is kind of tying back to your earlier illusion of giving a talk at the security seminar.
Yeah.
So the third component of the security triad is availability.
Yeah.
If I send at fixed interval updates to my coordinator, then I get availability guarantees or at least trivial detection for free. If I do whatever you are proposing, then it's entirely possible that a node drops off the network and I will never know.
Yeah.
I will predicting values that are entirely incorrect, but I never get corrected.
Yeah. So I
That's
think
good.
it's a bit, look at that, but I think it's a very good point. I mean, I have colleagues working on this crash detector, so it's exactly this. There is a trade-off. If you, here in this model, we focus just on the values, not on the fact that the node is active or not. Actually, one node could be generating 10 of those streams. And most likely it is. It's not just one value. So most likely, if you don't hear any of the streams, you can have kind of some kind of detection, says, perhaps I will ping the node, right?
Yeah. And then I guess the other question was, so a decade more ago, I talked to some people from Bosch. Are you familiar with like ECUs in cars?
Yeah.
Electronic control unit,
Yeah.
right? Communicating over CAN, everything is unauthenticated, unencrypted, it's terrible like it was in the 1970s.
Yeah.
And they said, sure, we could easily include encryption, but it's too expensive for computation.
Yeah.
So now you're starting to push models down into sensor nodes. Why are the manufacturers of sensor nodes not saying, well, that's nice and good, but this is too expensive for us computation?
Yeah, that's a very good question. I don't know. I think, I mean, I've been working with a project with Volvo for a while on this data compression. So this was at least used by their car to some degree. So it means that those sensors, they are not that simple anymore. And I think I haven't followed that much the discussion about CAN, but I think they are departing from that things of having a bus where everything is unencrypted. It's a little bit over. The vehicle systems you can almost consider like computer systems. They are complex, many sensors. Here we don't say exactly where we locate that thing. So most likely it's not on the sensor. It's at some aggregation level. It will be at the computing unit on the vehicle.
Okay.
So not on the ECU, right?
I'm wondering whether the approach can be used for cloud system monitoring.
Well,
the cloud system is highly dynamic, so the memory usages keep changing based on the workload and the update. And then the prediction is we just use linear prediction.
Yeah.
More accurate.
That's very good. So we want to check it out. That's definitely a use case we want to dig. You can have, of course, we don't claim that those models are very good. You can, of course, have much more complex models that will be. But here is more if you have a lot of values, a lot of different values to monitor, and you want to have a global view for cheap, basically. So I think I'm pretty sure that it is still useful in the cloud context. You want to monitor lots of machines, and you just want to have a good enough.
Yeah, but you have one coordinate, and in cloud you have thousands of nodes, and it's just you will overload this coordinate.
I mean, this is, I guess, logically one coordinator. Distributed cluster.
Yes.
Yeah. I think it would be a good practical use case to look at the cloud model.
Yeah. So typically, actually, what we have started. So here it's a logical coordinator because you want this global view, but since you don't have dependency between the nodes, you will have one dedicated coordinator proxy for every stream.
Yeah.
And then they will coordinate to a second level.
Other questions? Okay, let's thank the speaker.
Yeah.